So, what if I told you that the secret to making something incredibly strong is to fill it with flaws? It sounds completely crazy, right? But in the world of materials science, perfection is actually a weakness. Today, we're going to dive into the absolutely fascinating world of crystal defects, and we're going to see how these tiny, tiny imperfections are the real source of a material's strength and toughness. All right, let's start with a really simple question you've probably wondered about. Why can you bend a paper clip, but if you try to bend your coffee mug, it just shatters? I mean, they're both solid, right? But they behave in completely different ways when you put them under stress. Well, the answer to that mystery is hidden deep inside, down at the microscopic level. It's all about their imperfections. So here's our game plan. First, we'll hit this weird idea I call perfection's paradox. Then we'll build a quick catalog of all the different kinds of flaws. After that, we'll zoom in on the real star of the show, dislocations. We'll even figure out how to measure them. And finally, we'll see how this whole ecosystem of defects works together to make materials strong. Okay, let's just tackle this paradox head on. If you could somehow make a totally flawless, perfect crystal, yeah, it would be insanely strong. But, and this is a huge but, it would also be incredibly brittle. The second you applied enough force to break just one single atomic bond, the whole thing would just shatter. A catastrophic failure. It's actually too perfect to be useful. And this right here gets to the absolute heart of the matter. You see, material properties really fall into two big camps. You've got your structure-insensitive ones, like melting point. Those are just baked into the chemistry of the material. But then you have the properties we really care about as engineers, things like strength and toughness. Those are structure-sensitive. And what are they sensitive to? You got it, defects. So here's the big takeaway. Materials engineering isn't about a quest for some impossible perfection. It's a science of controlling imperfection. We don't try to get rid of flaws. We actually introduce them and arrange them on purpose to get the properties we want. We literally engineer the flaws to build strength. Okay, so if we're going to engineer these flaws, first we need a way to organize them. And it turns out the most logical way to do that is by their shape, or more precisely, their dimensionality, whether they're a point, a line, a surface, or a whole volume. So here's our catalog. First, you have your 0D point defects. Just think of a single atom missing or in the wrong spot. Then you have 2D planar defects, which act like big walls inside the material. And you even have 3D volume defects, which are kind of like tiny pebbles stuck inside. But for our story today, where all the action really happens, that's what the 1D line defects. All right, let's zoom in on those 1D line defects. We call them dislocations. And these are the engines of plasticity. They are the entire reason a metal can bend and deform instead of just shattering into a million pieces. So what exactly is a dislocation? You know, the best analogy is trying to move a giant, heavy rug. Instead of trying to pull the whole thing at once, what do? You make a little wrinkle in it and you just push the wrinkle across the floor. It's way easier, right? A dislocation is exactly that, just on an atomic scale. It's a moving wrinkle that lets the material deform without breaking all its bonds at once. Let's meet our first major type, the edge dislocation. The easiest way to picture it is to look right here. It's like someone took an extra half sheet of atoms and just jammed it into the crystal lattice. Now, the absolutely crucial thing to remember here is that the dislocation line, that bottom edge of the extra plane, is perpendicular to the direction the atoms are trying to slide. And our second type is the screw dislocation. Okay, this one's a little more trippy to visualize, but the key thing is that it creates this kind of spiral ramp in the crystal. You can see how the atoms form a helix around that center line. And its core feature? The dislocation line is parallel to the direction of slip. This table just breaks it down nicely, side by side. You can see the different symbols and all that, but honestly, the only row you really need to care about is the vector relationship. For an edge dislocation, it's perpendicular. For a screw, it's parallel. That one little geometric difference, well, it changes absolutely everything. So why does perpendicular versus parallel matter so much? Well, think of it this way. An edge dislocation is basically stuck on a railroad track. It's locked onto one single plane. But a screw dislocation, it has a kind of superpower. Because its vectors are parallel, it can do something called cross-slip. It can literally jump from one plane to another to get around obstacles. And that ability is what makes complex metal forming possible. Now, time for a little reality check. In real materials, things are never this neat and tidy. Dislocations are almost never 100% pure edge or 100% pure screw. They're actually complex, curvy lines that change their character as they go. You see that beautiful tangled mess in the image on the right? That's what the inside of a real metal actually looks like. Okay, so we get what dislocations are, but this is science, and in science, we need to be able to measure things. We need a way to describe the exact size and direction of the distortion they cause, and for that, we have a tool called the Burgers vector. The Burgers vector, which we just call B, is basically the unique fingerprint or ID tag of a dislocation. It tells you everything you need to know about the distortion. And get this, no matter how a dislocation line twists or moves through the crystal, its Burgers vector stays constant. It's a conserved quantity, which is incredibly useful. So how do we find this vector? The idea is actually pretty cool. Imagine you're in a perfect crystal, and you take a walk, say 5 steps up, 3 steps right, 5 steps down, and 3 steps left. You end up right back where you started, right? But now try to do that exact same walk around a dislocation. Because the lattice is all distorted, you won't end up back at the start. You'll be off by a little bit. That little vector you need to draw to close the gap, that is the Burgers vector. It's the physical measurement of the imperfection. And this leads us to a really powerful rule of thumb called Franck's rule. See, dislocations can't just appear out of nowhere or vanish into thin air inside a crystal. So when several of them meet at an intersection or a node, the sum of all their Burgers vectors has to equal 0. It's just like with pipes or electrical circuits, whatever flows in must flow out. Okay, we have covered a ton of ground. We've talked about different flaws and even how to measure them. So for this last section, let's put all the pieces together. Let's see how this whole ecosystem of defects interacts to create the strong, useful materials that build our world. First off, let's connect the micro to the macro. The movement at a single dislocation, totally invisible. But when you bend a piece of metal, you're not moving one. You're moving billions upon billions of them, all in a coordinated way. And that massive coordinated movement actually creates visible lines on the material's surface. We call them slip bands, and they're the macroscopic proof of this amazing atomic-level dance. And this brings us to the grand synthesis. This is where it all clicks. Strength is not about having no dislocations. Strength comes from controlling their movement. It's about making their lives difficult. So what we do as materials engineers is we deliberately use all the other defects in our catalog, the point defects, the grain boundaries, the precipitates, and we use them as microscopic roadblocks. And the more we make it harder for those dislocations to move, the stronger the material gets. That resistance to movement, that is strength. So we end right where we began, but hopefully with a totally new perspective. Imperfection isn't some flaw to be avoided. It's our single greatest engineering tool. Which leaves us with one last thing to think about. If deliberately controlling flaws is what creates strength and usefulness, what does perfection truly mean when we design the world around us?